Welcome, Felix, with the first talk of today's session. Have a screen.
Thank you very much for organizing this nice workshop. So, my talk will be about high-order diagrammatic extension around BCS, more particularly the polarized superfluid phase and the effective Hubbard mode. This work was done together with Gabriele Spada, who was our postdoc and is now in Central. My colleague Chris Guinness, Riccardo Rossi, Peter Singularity, and Michel Werner. And there is a preprint which contains most of what I'm going to do in section. The next version will contain more. So, as you can see from the title, it's not really about impurities. But if I look at the short version of the title of the program, I can argue that it fits anyway. So in 1911, so 210 years ago, superconductivity was discovered experimentally. And then quite a bit later, there was BCS theory. And now we turned BCS theory into an exact approach, as I will try to explain. So the general motivation is unbiased approaches for fermionic and body problems, which is of course relevant to many fields because strongly interacting fermions are everywhere, from solids and molecules to electrons to nuclei and neutron stars, where it's nucleons, and also the quarks in QCD. And of course, the big challenge is to do reliable computations, unbiased computations for a large number of fermions, and usually even in the thermodynamic limit, where the number of fermions goes to infinity. So analytically, you can do a lot of things in one dimension, also for few body problems, and in weakly correlated regimes. But outside of this, you mostly have to turn to numerics. So a quick word about the one kind of method which is very popular and successful nowadays, which is the family of tensor network approaches, which work usually extremely well in 1D. In 2D, it's getting more difficult to get unbiased results. In their case, they need to extrapolate the so-called bond dimension to infinity, which is not so often possible. And in 3D and also in continuous space, there is really not much yet, and it's probably very hard. So the most widely used kind of approach is what I would call here bulk Monte Carlo approaches, which are all based on some kind of mapping from the quantum problem in d dimensions in a finite volume L to the d onto a kind of classical problem with one extra dimension, which is the imaginary time. And accordingly, the volume is multiplied with beta, which is the size on the imaginary time direction, which is the inverse temperature. And there are several kinds of such approaches, which correspond to several kinds of this mapping. One of them is path integral Monte Carlo, where each of the n fermions gets a sort of classical trajectory as a function of the imaginary time. Then there is auxiliary field QMC, also known as lattice QCD in the QCD context. And there is also a determinantal diagrammatic Monte Carlo, which is very different from what I will be presenting, because there it's both connected and disconnected diagrams. And this method is also known as CT-int in the context of DMFT. So for all these methods, except in special cases, there is the fermion sign problem, which leads to an exponential increase of the CPU time as a function of the number of fermions. And in short, this is due to the following. In these approaches, you will write a quantity Q, a physical quantity Q that you're interested in. You will write it as an average, which looks like this. C here is the configuration. And W of C is a weight, but this weight is not positive. It can be both positive and negative, depending on the configuration C. And even if typically we are interested in some local observable, so that this Q, this calligraphic Q of C here, only depends on this central part of the configuration C. If there is a small change of the configuration very far away, for example, for path integrals, two fermions which are very far away exchange with each other, and this can easily change the sign of W. So the sign of W is a sort of an unphysical sensitivity to the configuration very far away. But we know that physics is local. So that's clear, for example, from the fact that if you want to compute some intensive quantity Q, then it's well defined even in the thermodynamic limit. So obviously that means that actually what happens very far away doesn't matter. And this is true even in the presence of long-range order. Indeed, let's consider, for example, the 3D-XY model below TC from the ferromagnetic phase. In principle, the average magnetization is 0. But if you take the correlation function at large distance, and you also take the thermodynamic limit, this is non-zero. So that's when you have long-range order. So it looks like these two spins, which are very far away from each other, they are correlated because the expectation of the product is non-zero, while the expectation of each of them is 0. However, this correlation can easily be removed by working in the broken symmetry point of view, where you introduce some external field, let's call it eta, along some arbitrary direction. And then you redefine the notion of average by saying that you take the average with this field eta, and then you take the limit of eta going to 0. And you also take the thermodynamic limit first. If you do that, now you have a non-zero expectation value for the magnetization. And now the two guys are not correlated anymore. So that's something that we're also going to use. So in general, the kind of approach that we are using is diagrammatic Monte Carlo with connected diagrams. So the basic idea is very simple. We sum up all connected Feynman diagrams of order n smaller than some n max. And then we increase this n max. And in the limit of infinite n max, the truncation error coming from the fact that we truncated the diagrammatic series at n max, the truncation error will go to 0. This works directly in the thermodynamic limit. I will come back to that. So, of course, we don't have the usual kind of scaling with system size that you have in these bulk QMC approaches. Also, the diagrammatic technique is very flexible, and we can use that. So we can change the starting point of the expansion, the order 0 of the series, and we can reorganize the expansion by using dressed propagators or vertices, making the diagrammatic series non-perturbative in the sense that it's not just a simple expansion in powers of the interaction. So these are the standard tools of diagrammatic technique. And typically they are used at low orders. And they typically already give pretty good results, qualitatively correct, and even quantitatively not very far off. That's why they are used very widely already at low orders. But here, what we do is we go to high orders and try to reach the regime where it becomes exact. Moreover, in this case, the Thermodynamic sign is actually helpful because it leads to strong correlation, cancellations between different diagrams. So that at large order, even though there is a very large number of diagrams, factorially large number of diagrams, the contributions at large order are strongly reduced. So formally, the setup, the general setup is as follows. So starting from some physical problem with some action S, you first introduce a formal expansion parameter psi and correspondingly action S psi in such a way that at psi equals 0, the action is quadratic. At psi equal 1, you recover the original action and should be an analytic function of psi. Then to compute some physical quantity Q, which a priori is some expectation value taken with the physical action S. Well, you first replace S with S psi so that your quantity Q now is a function of psi, which you can then expand in powers of psi. And to get the physical result, because of this condition, we should set psi to 1, which in the simplest case, where the series converges, just means that we should sum up these Taylor coefficients Qn.
Felix?
Yes.
People come here, you are unable. Try to shift the microphone to the center. Yes, not, you don't need to put it in, but kind of.
Yeah, this thing is really terrible. Okay. Sorry about that. So in practice, this Qn is a sum of all order n connected Feynman diagrams. And because it's connected, it's well defined in the thermodynamic limit, as we will see in a moment. So in practice, here is an example of a connected Feynman diagram. This one is for the density. You have to assign some position and imaginary time, r and tau, which we collectively denote by big X, for each of these internal vertices. And then you have to integrate over them, which means sum over r and integrate over time. And then you should sum over all possible topologies. So the key point is that because these topologies are connected, and because each of these propagators decreases to 0 at large distance, this integrand here, which is just a product of all these propagators, goes to 0 whenever one of the vertices goes to large distance. So that's why this integral remains well defined in the infinite volume, in the thermodynamic limit. So as I said, there is a big freedom in choosing the starting point as naught. Several options have been already explored. And here we will use S naught, which breaks the U1 symmetry. A few words about the Monte Carlo algorithms that allow to efficiently calculate this Qn up to pretty large n. So there is one kind of algorithms which for many body problems was introduced in 2010, where configuration C is defined by both the values of the internal variables and a given topology. So here you typically say pick a propagator line and then two propagator lines and propose to exchange the endpoints, for example. And then the Monte Carlo weight is just taken as the absolute value of this integrand. Another kind of algorithms was introduced by Riccardo Rossi. And there, a configuration is just given by the set of internal variables. And the weight is now given by the absolute value of the sum over all topologies of the integral. And this sum is done exactly with machine accuracy. Actually, diagrammatic Monte Carlo was introduced before for Polaron problems by Prokofiev and Svistunov, first for bosonic Polaron problems, so electron phonon, and later for a fermionic Polaron, so a mobile impurity in a Fermi sea. And more recently, we also introduced a determinantal algorithm for the fermionic case. And Chris will be talking about that in this program, and also Nikolai will talk about another work on Polarons. Also, there is another kind of algorithms about real time. So far for Anderson impurity problem, and they use the Keldysh representation and also determinants. So there are some analogies with the CDET algorithm, which was introduced earlier actually, and Xavier will give a talk about this. So what about the computational complexity? There was a sort of prejudice that fermionic problems are always computationally hard, somehow exponentially hard, but actually that's not true. So the CPU time, of course, increases with the diagram order, and with the old algorithm it increases factorially, with the new one exponentially. But on the other hand, if the series is convergent, which is often the case for fermions, then the contribution itself decreases exponentially with order. So yeah, it's exponentially hard to go to high orders, but because of this exponential convergence, actually you don't, in a way, you don't need to go to very high order to get an accurate result. So in the end of the day, for CDET, it's just a power law, it's polynomial scaling of the CPU time as a function of the total error epsilon, which is a sum of the statistical error and the truncation error. So here is just a subset of results that were obtained in the last years with diagrammatic Monte Carlo and CDET. I don't think I will go through the list. It's the typical relevant models for condensed matter and also for cold atoms. Maybe for this community, I should mention that there are works on electron phonon, not only single polaron, but also for the many body problem, or many polaron if you want. So all of this is actually in normal phases above the critical temperature, or sometimes there is one exception, which is a work on the Haldane model, which includes some calculations in a magnetically ordered topological phase. But they're actually, for experts, they use the bold approach, and we're not going to use it here. So physically here, what is new is that we will study a superfluid, or in other words, superconducting phase. So we study the simplest model, which has a simple S-wave superconducting phase, which is the attractive Hubbard model on the 3D cubic lattice. That sounds like a good idea. So then I just forget about this one.
No, we'll try to compensate. So continue, and guys, write me in chat whether it's improved with this second microphone.
But I guess I can just forget about this one and just switch to the other one.
Just go and write me in chat.
Okay. So so the Hamiltonian of the Hubbard model, as you know, has a kinetic part, which is the nearest neighbor hopping, chemical potential. So here we allow for different chemical potentials for up and down. And then interaction part, which is on-site interaction, and for us, U is negative. Now, how do we set up a diagrammatic expansion in the superfluid phase? So it's the S-wave superfluid phase. So the order parameter is just this one. So destroy two fermions on the same side with spin up and down. And in order to access this phase, we use the following unperturbed quadratic Hamiltonian, which breaks the U1 symmetry. So our H0 is the original kinetic term, the hopping term. Chemical potential terms, actually the chemical potentials are shifted. That's a standard technical trick. And the key point is that we add this symmetry breaking pairing term, which has the usual BCS form with a prefactor that I will call delta 0. And then we should introduce our formal expansion parameter psi. And we do it in the simplest possible way by taking h psi to be a linear function of psi. Of course, such that when psi is 0, we have h0, this quadratic Hamiltonian. And when psi is 1, we recover the original h of the Hubbard model. And then we follow the standard procedure. So as I introduced before, to compute some quantity q, we make it psi dependent by computing it with this h psi, and then expand in powers of psi and compute these coefficients qn. We will also be interested in the pressure, in other words, the thermodynamic grand potential per unit volume, defined in the usual way as the log of the partition function. And for this guy, to make psi dependent, naturally, we just replace here h with h psi, and then expand in powers of psi. So here is an important observation. In this h psi, you have 1 minus psi in front of h0, and h0 is the one which contains the symmetry breaking term. So you see that effectively in this h psi, there is a symmetry breaking field, which is delta 0 multiplied with 1 minus psi. Such that, of course, at psi equal 1, this symmetry breaking field is 0, and we recover a Hamiltonian which does not break the symmetry. So this is just, again, the explanation of why. So h psi contains this 1 minus psi times this h pair delta 0, which is nothing else than h pair with delta 0 times 1 minus psi as the symmetry breaking field. So let's see a little bit at what to expect, depending on whether we are above or below TC, and also depending on whether we break or we don't break the symmetry. So whether we take delta 0 equal to 0, or non-zero. So the standard situation, which is what has been done in basically in many papers before, as I mentioned, is this one. So you are in the normal phase and you don't break the symmetry. And then everything is fine, at least in some part of the phase diagram. So your Q of psi is an analytic function of psi. There is no singularity anywhere here. And therefore, you can get the correct result by either by summing up the series, or if it diverges, if there is some singularity, for example, over here on the left, then you can resum it. However, if you are now in the superfluid phase below Tc, and you still do this expansion without breaking the symmetry, then you have a problem. Because at psi equal 1, you are at the physical point where it's superfluid, because we are below Tc. Whereas at small psi, you are in the normal phase. Because when psi is small, actually the interaction is also small because it's multiplied with psi. So you are normal at finite temperature. So that means that you must have some phase transition as a function of psi, some singularity between 0 and 1. And therefore, the series will not only be divergent, but also not resummable. So mathematically, that means it's hopeless. And that's why we are breaking the symmetry using this non-zero pairing field in our H naught, in our starting point of the expansion. First, let me note that if you do that and you are above Tc, it will still work. Because the order parameter has to vanish at psi equal 1 at the physical point, because we are in the normal phase. But there is no singularity here. The order parameter will just cross 0. And everywhere you are in a normal phase, or if you want, you can call it para-superfluid by analogy with a paramagnet. So here there is no singularity and the series will converge as well. Now, the case that we are really interested here is this one, of course. So we are below Tc. And now, with this delta 0 non-zero, we remove this singularity. Because now we are in the superfluid phase everywhere for all values of psi between 0 and 1. The order parameter as a function of psi will look like this. And it will have a non-zero limit at the physical point here, which corresponds to a vanishing symmetry breaking field. As you will see, actually here, also in that case, we can sometimes still get results, namely in the metastable regime, where the normal phase is metastable. And then, as I will show later, this singularity is very weak. And so even though in principle, the series should diverge and be not resummable, in practice, it behaves as a convergent series. And we can get also results in the metastable regime in this way. A few words about the calculation of the order parameter. So when Q here is the order parameter, then this expectation value here with H psi is this one. And then following the general rule, we should send psi to 1. Here, actually, it matters that it's 1 minus, because you see that the order parameter is a function of psi. If we take psi going to 1 plus, it will have the other sign. So here we take it to 1 minus, because this is what we can get by analytic continuation of the Taylor series. That's just a technical point. Another maybe more fundamental remark is that since we are in a situation of spontaneous symmetry breaking, we should actually take the thermodynamic limit before taking this limit, which corresponds to a vanishing external field. And so it just means that when we compute these coefficients of the Taylor series, which we then sum over the order, because as we will see, our series is convergent, then in principle, one has to take the thermodynamic limit before doing the summation to infinite order. Finally, I should say what we choose for mu naught, these shifted chemical potentials, and also for delta naught. So the most natural choice is just to take them from the BCS mean field theory. So mu naught is given by the standard Hartree shift, and delta naught is given by the standard gap equation of BCS theory. We also sometimes use other values of delta naught, but we will always keep this choice, simple choice for mu naught. This is how the diagrams look like for the order parameter. So you have these anomalous propagators where particles are destroyed or created at both ends because our H naught does not conserve the number of particles. So this is the order 0 for the order parameter. And these are the first order diagrams. And actually they cancel out each other if we take the mean field delta, because then because of this gap equation, these counter terms exactly cancel these tadpoles. Here is an example of order 9 diagram. So I want to notice here that as I mentioned in the general case, here we can take the thermodynamic limit because diagrams are connected and the propagators decay as a function of time. And so in our calculation, large distances only give small contribution. So this is more physical than the situation for a bulk QMC. And this is all because we are working in a broken symmetry point of view. So we removed these spurious correlations at infinite distance. So in terms of the algorithm, we use the Rossi's connected determinant algorithm. The only difference is that here we have to use number propagators, meaning that propagators have this standard 2x2 matrix form, like in BCS theory, where on the diagonal you have the normal propagators, and off diagonal you have the anomalous propagators, where you either create 2 particles or destroy 2 particles. So in a few words about this CDET procedure. So the idea is the following. You have to compute this ON, say for the order parameter, which is the sum of all diagrams of order n, connected diagrams. And as I mentioned before, here what you do is that you do these integrals over by Monte Carlo, but you sum over all topologies in an exact way for each value of these internal variables. So actually at each Monte Carlo step, you pay quite a big price to sum over all topologies. But the point is that you don't need to pay a factorial time to do that, even though the number of diagrams is factorial. And the reason is that there is a simple recursive formula which expresses this thing that I call CDET here, which is a sum of all connected diagrams, in terms of the determinant of some matrix A. So computing a determinant, of course, is very cheap. It's just the power law as a function of the order, which is the size of the matrix here. And then you subtract disconnected diagrams recursively, and it turns out that it only costs 3 to the n operations. So it's much cheaper than n factorial.
So is it the disconnected diagrams that give you the exponential scaling? But the determinant is extremely cheap.
Yes, so you immediately get 2 to the power n because you need to remove In this thing here, you need to partition the set of all vertices into two parts, the part which is attached to the external point and the rest.
Yeah.
So this gives you already 2 to the n possibilities.
Yeah.
And then when you do this recursively, it turns out that it's 3 to the n.
Right.
So this big matrix A is simply the propagator matrix of the propagators in terms of these NAMU blocks, which connect the vertices to each other. There is a last row and last column which depend on the observable. So in the case of the order parameter, it looks like this. It doesn't really matter. And on the diagonal, so you have zeros because of our choice of the chemical potential, which removes all the normal tadpoles. And here, the off-diagonal parts of these diagonal blocks, they are also zero in the case of delta mean field. Numerically, our code is based on a library not yet released, but at some point it will be released. Very nice C++ library by Carlo and Fedor Simkovic, which also implements a new kind of Monte Carlo, which they present in this recent preprint. Now to the results. So in general, we have different chemical potentials for spin up and spin down. Mu here is the average chemical potential, and H is the Zeeman field. Hopping is 1. We pick an interaction strength, which is -5. Average chemical potential is fixed to some value, which is chosen in such a way that the total density is close to 1/2, so quarter filling. And when the Zeeman field is 0, that's one of the special cases where QMC approaches are sign-free. So there is, for example, this data for the critical temperature in the literature. So at 0 Zeeman field, so I will call it TC0 as a function of the interaction strength. And you see that our choice of 5 is really within the strongly correlated regime of the BCS-BC crossover. It's not far in the far BCS regime at weak coupling where TC is exponentially small. And numerically, the value of TC here is 0.25, which corresponds to 0.06 TF. So first, to do a benchmark and check that our approach is working, we compute the order parameter at 0 Zeeman field so that we can compare to another method. And at some temperature, which is roughly 1/2 of TC. So here is the data for the partial sums for the order parameter as a function of Nmax. Nmax, I remind you, is the maximal diagram order, which in principle should be extrapolated to infinity. So you see that indeed it looks convergent. It doesn't converge very quickly, so we need to extrapolate. So for that, we can, for example, just use PADE. So here I show the 3 diagonal PADEs, 4, 4, 5, 5, and 6, 6. You see that they give results which are close to each other. And from these 3 points, we can claim a result with a conservative error bar like this. You can also cross-check by changing the value of delta 0. So going away, sorry, I forgot to mention, this was for the mean field choice of delta 0. But we can also take other values of delta 0. And then we get, of course, different series, but they will extrapolate to the same result within error bars. So these are the PADEs for these different delta zeros. So we can be already quite confident in our CDET result shown here. And then we cross-check with a completely different method. So we use the Ddmc method with the code provided by Evgeny Burovsky. So in that method, the control parameter that you should extrapolate to infinity is the system size, as in all, I would say, bulk QMC approaches. So now these purple data from DDMC are plotted not as a function of Nmax, but as a function of L, which is the linear system size. And you see that actually in this case, the finite size effects decrease very quickly. So it looks like we reached the thermodynamic limit already here, and it's perfectly consistent with the CDET result, which is obtained directly in the thermodynamic limit. So that was the benchmark. Now we go to the polarized regime, so non-zero Zeeman field, where there are no unbiased results available because of the sign problem. The expected phase diagram topology in this regime where U is not very large and discarding FFLO phases, I'll mention that in the end, is the following. Based on BCS mean field theory and also some DMFT calculations, and also actually cold atom experiments, even though they are done in continuous space so far. So no optical lattice, so it's not the Hubbard model, but the physics can be expected to be similar. So maybe shall I just remove this thing because and I'll just use this? Because I think this probably is still annoying people.
People don't complain. I check and chat, and I don't see complaints.
Because people, the thing is, I can just use this mic, which I think would be better.
When if you turn your head from it.
I'm not turning my head, and I'm always looking at the same point.
Up to you. So far, people don't complain.
Let's just do an experiment. Even though we are theorists. So let me just get rid of that and just do it like that. So so the phase diagram as a function of temperature and Zeeman field. So at zero Zeeman's field or small Zeeman field, there is the standard second order phase transition from superfluid to normal. But here actually this phase transition line is expected to become first order. And sorry. At zero temperature, the superfluid is expected to remain completely unpolarized up to the critical age where there is the first order transition to the normal phase. And this is just because of the single particle gap. So to check this, we will do such a scan as a function of h at a fixed temperature, which is about 1/4 of TC now, of TC0, I mean. And in order to look for this first order transition, of course, we should calculate now the thermodynamic grand potential, or in other words, the pressure. So here it is as a function of h. The blue points correspond to the superfluid phase. They are obtained by taking the mean field delta, non-zero delta. And the green points correspond to the normal phase, and they are obtained by just taking delta 0 equal to 0, so without breaking the symmetry. And you see that indeed the two curves are crossing. So as expected, as a function of h, here the superfluid phase is the equilibrium one, and then it switches to the normal phase. Well, we can get a pretty accurate value for this critical age, which turns out to be 2 times smaller than the mean field value. So these curves are the results from the mean field BCS theory. Here are the partial sums for the pressure at this particular value of h. You see that here actually the convergence is much better than for the order parameter. We almost don't even need to extrapolate in order to get a very accurate result for the superfluid series here in blue. For the normal series, we can not go to that amazingly high order. Order 13 is really amazing, by the way. If you would try to do it by enumerating diagrams, it would take you completely unreasonably large time. But here we see that we can do it. And for the normal phase, it's actually more difficult to go to high orders. And this we just attribute to the fact that the propagators in the normal phase have no gap, so they will decrease much more slowly as a function of distance. So for large system size in the normal phase at low temperature, you suffer, while for the superfluid series, you have the gap. So the propagators always decay quickly with distance. Note that at this point, actually, we are in the superfluid metastable regime. We checked, I don't show the data here, but we checked that the order parameter is still non-zero, so it's really still superfluid, even though it's now metastable. And the normal phase is the stable one. So you can be a bit puzzled about this metastable regime because, as I argued in the beginning, in that case, the series should diverge. And indeed, it diverges, but the point is that it diverges slowly because, as usual with first-order transitions, if you are near the transition, then you have a large energy barrier to go from the metastable to the stable phase. And accordingly, as a function of the psi, or in other words, as a function of the external field, you have a weak essential singularity. So this is quite well known in the literature. The singularity is supposed to be some weak non-analytic behavior like that. So an exponentially small discontinuity through the branch cut. And from this, we expect that the large order behavior will look like this. So yes, it will diverge. But if psi c is close to 1, if we are only weakly metastable, then this will diverge slowly, whereas this thing will quickly go to 0. So therefore, in practice, it behaves like a convergent series. And this is what we observe. So just a quick recap. So this is, again, the phase diagram. I showed you the scan here at fixed temperature as a function of h, where we observe the first order transition. And I also talked about this situation where the superfluid is metastable. And now I will show you some data at this point. So a significantly higher temperature, but still in the superfluid phase, where now we can observe a polarization of the superfluid phase. Whereas here, the polarization was still 0 within the arrow bars, as expected at low temperature. So in order to see this, we directly compute the magnetization, so density up minus density down. And these are, again, the partial sums as a function of the maximal order. So here you see that if we take the mean field delta, then we get these purple points, which are absolutely useless and impossible to extrapolate to infinite order. However, if we tune delta 0 significantly away from this mean field value, then we can get different curves which now look convergent and actually, well, it's not shown here, but if you zoom, you see that they are really consistent with each other. So from this, we can claim a result for the magnetization, which is basically this with this arrow bar, which corresponds, if we divide by the total density, to a 4% polarization. So it's a small polarization, but we can clearly see it. And actually, the BCS mean field result is, of course, this order 0 from the purple series. And this is even much smaller. It's the exact result divided by 30. So this is why the mean field series here is not good at all, because mean field is a very bad starting point. So in this regime, where you have a weakly polarized superfluid, polarized due to the combination of Zeeman field and finite temperature, of course, it's the natural thing is to do a simple quasi-particle description. So let's just write down a simple Hamiltonian, effective Hamiltonian, for this situation in the regime where the temperature is low enough, of course. So this is just a quadratic Hamiltonian where we have fermionic quasi-particles with some dispersion relation. We don't really know what it is, but it doesn't matter. the only key point is that the dependence on H on the Zeeman field is simply given by this expression, where this EK is independent of H. And this basically follows from this commutation relation. So in other words, the fact that the quasi-particles carry a spin 1/2. Then once you have this simple quadratic Hamiltonian, you can of course easily compute the magnetization. It will just be given by this difference of Fermi-Dirac distributions. Actually, we are in a regime where the quasi-particles are dilute enough so that we can forget about these Fermi statistics. And then the expression simplifies, it factorizes like this. So the dependence on H is just this sinus hyperbolic. And here you have the density of quasi-particles, of thermally activated quasi-particles at 0 Zeeman field. There is, of course, a lower bound on this dispersion relation of quasi-particles, which is by definition the single particle gap. And accordingly, there is an upper bound on this density of quasi-particles, like this. So here is a plot of our results for the magnetization, M, so it's N up minus N down, as a function of H. So this was the point that I showed you before, and these are the results now if we change H. And you see that it's pretty well fitted by the simple formula from the previous slide, from the quasi-particle model. And with one fitting parameter, which is the density of quasi-particles, which is of course very small, but we can clearly resolve it. And from this, we get an upper bound for the gap. And this is actually consistent with the value for the critical H that we got, because of course this critical H should be smaller than the gap. Finally, let me discuss a bit about the large order behavior of the superfluid series. So remember that 1 minus psi plays the role of the symmetry breaking field. And accordingly, the order parameter as a function of psi will have a finite limit when psi goes to 1, which is by definition the physical order parameter. But then actually it's known in the literature that there is a square root singularity. So this curve here has an infinite slope for any temperature below Tc. And this is due to the Goldstone mode. There is also a formula for the prefactor in terms of the superfluid stiffness. So from this square root singularity, if you expand now this in powers of psi, then naturally you get a power law tail for the large order behavior of the Taylor coefficients with an exponent 3/2. And for the pressure, because it's an integral of the order parameter, the exponent is 3/2 plus 1, so 5/2. So, I mean, first of all, this already kind of explains why the convergence that we saw for the order parameter was not very fast. And now here is the data for the pressure. And now, first of all, in the log linear scale. And you see that it doesn't look like a straight line at all. So meaning that indeed it's not an exponential decay. The decay is slower than exponential. This is just for some value of temperature and H, which actually correspond to the point where I computed this magnetization of 4% just before. So now on the log-log scale, it looks nicely linear. So it looks like indeed it's a power law. However, the exponent seems to be different from the expected 5/2, which is shown by the blue line here. But a more careful analysis shows that actually our data are not perfectly linear to the point that we cannot reliably extract an exponent from them. Moreover, it turns out that this prefactor here, even though we don't know exactly the stiffness, but we have some estimate from the MFT, this exponent is apparently very small. So so that on our scale here, it would be really outside of the plot, way below. So therefore, apparently what's going on is that in order to reach this true large order behavior with this small prefactor, we would need to go to even much higher orders. So what we see here is not yet the true large order behavior. But in practice, it doesn't really matter because anyway, this prefactor is very small. So it will only give a small contribution to the final result. And so in practice, as I said, for the pressure, you don't really even need to extrapolate because the series is convergent very quickly. So what we would be interesting to do next, of course, replace the bare vertex U, which we have used so far, with a dressed vertex, which includes the ladders. And in the normal phase, it was already shown how to do it with CDET. And this would allow to go to the strong Klopling regime, where it's expected to have a polarized superfluid even at 0 temperature, also known as a breach pair phase. Then, of course, there is a big question about FFLO phases. According to BCS mean field, yes, it occupies a large part of the phase diagram. So in order to address this question, in principle, it's straightforward. We just need to make our delta 0 space dependent. Of course, 2D is also interesting. Of course, now at finite temperature, it should be algebraic order. But maybe the same kind of approach can work anyways. And for D-wave superconducting order, in principle, it's also easy. One just should introduce a delta 0, which is dependent on the relative momentum of the fermions in the pair in this way. In continuous space, where there are a lot of experiments, of course, we can get it either by extrapolating the filling to 0 or by working directly in continuous space, as we have already done in the normal phase. But then probably the convergence radius will be 0. And the question is whether it's still Borel resummable. We have seen in the normal phase that it was the case. And finally, also the method could be useful in nuclear physics, where people from CEA, actually next door, have already observed that a similar expansion to what we do here, so around the broken symmetry BCS mean field, already yields promising results at order 3. And for this kind of calculation, one remark that I would like to make is that we recommend to perform the Monte Carlo in position representation differently to what has been done in this recent paper about chemistry and materials. Thank you for your attention.
So just one curiosity, is it possible to compute also Green's function, or like with this diagrammatic Monte Carlo? I guess to see, for example, the difference.
Green's function as a function of imaginary time.
Yeah.
Yeah, sure. It's absolutely straightforward. So it's basically we almost don't need to change anything. So here we compute the Green's function as at imaginary time 0 to get the basic observables. But we just
do you have a sense
finite
of
imaginary time is straightforward, and that would be interesting, for example, in order to directly get the gap.
Yeah, and now does the density of state changes from the BCS standard BCS shape?
Yes, so indeed the gap apparently the gap is very different from the mean field one, because as you have seen, the polarization is very different. Yeah. This is directly related to the gap.
Mm-hmm.
Question from online. Questions from online people.
Can I ask a question, please? Hello?
Yes,
Do you-
go ahead.
Why did you start from 3 dimensions? Isn't it more natural to start from 2 dimensions?
Well, I think it's more natural for in 3 dimensions because there we have long-range order and spontaneous symmetry breaking. In 2 dimensions at finite temperature, I'm not really sure whether exactly the same approach will work. Maybe it will work, but I don't know. It's not immediately obvious to me because now you see we are breaking the symmetry, but in the end, the physical state actually does not have long-range order. I think it will still work, but I would it's less it's maybe more difficult numerically.
Yeah, I see. Thank you.
Yeah, I actually in practice for practical reasons we do it in a finite box, so I swept it under the carpet. But actually we use just a large finite box. Check that. Yeah, thanks. That's a good. I think that's a good observation. Yeah, so probably it can help us to use a box which is not too large. Yeah, I agree. And then if we are interested in not interested in the correlation function at very large distance, but in some typical observable or correlation function, say at a reasonably large distance, then the size of the box will still not matter. Yeah. Very good suggestion. Yeah. Indeed.
Okay. No other questions from the audience. If not, we'll stop recording this session. Thanks, Felix.